All right, there's a few little fun facts. This will be a short video, but I thought I'd throw them in somewhere here. We've talked about non-contact forces. The beauty of doing force analysis is you pick an object, you do a free body diagram, you look for the things touching it. The only other thing that we need right now in mechanics is the force of gravity, which comes from the object of Earth, if we're on Earth, or Moon if you're on Moon, or Mars if you're on Mars, or whatever. So, kind of cool thing that we're not going to use right now, but you will study a bit of in your studies of physics, is that all forces seem to, as they come from or come down to the 5 fundamental forces, non-contact forces. If you learn your chemistry or atomic physics, when I touch something, I'm not really touching anything because 2 electrons can't actually occupy the same state. So, but then there's all kinds of interesting things there. But nonetheless, it's an electrical force. We call it a contact force and not get lost in it. So it's we talk about these 5 non-contact forces: action at a distance, action without touching. And it's kind of cool. As far as we know right now, there seem to be 5. There's gravity, the electric force, the magnetic force, the nuclear weak force, called the weak force, and the nuclear strong force, called the strong force. Not very imaginative names, but that's the name of the force. Okay. So in the 1800s, people studied the electric and magnetic force. And they came up with the idea of fields, and that is, how does one thing pull another thing? Well, it must create a field. It's kind of like a sound field. I call out and say, hey, come here, to my dog, and he hopefully comes. So electric and magnetic forces were studied in earnest in the 1800s, and around the mid-1800s, they realized that electric and magnetic forces were connected. We call it electromagnetism. So there are 2 aspects of fundamentally the same things, but there are different behaviors that you learn about. But still, they're fundamentally connected, and that leads to one of the nature of light. So about mid-1800s, these 2, it's like, they're not really 2 entirely distinct things. They're connected. Then, it's natural to think, is there one force? Is there one love? Is there Bob Marley? So we say, all right, there's the electromagnetic force. We got that. And study nuclear processes. And this was happening more in the 1900s. And we had these inside the nucleus of an atom, the weak force and the strong force related to radioactivity, radioactive decay, and things like that. And it turns out that there is a connection between these 3, hence purple. And that is called then the Electroweak Force. Around the mid-1900s, that was understood how that connection happened, and even when those kind of separated in time. I won't go into that. But there's some deep connection there, which is very provocative. You're going, hey, we're on the right track. Now, Einstein was interested in this, and how could you not be interested in connecting all of them? But really, if you just look here, what is that strong force? What is it? It's the thing, this is the thing that holds a nucleus together, because protons and protons push each other apart electrically, and neutrons in the nucleus don't care. They don't play electric games. So it's this strong force, so that's interesting. So maybe all these are connected. And so we don't know if it is at this point, but we call it the grand unified theory, or grand unified field theory, GUTS. So we start getting biological here. We got GUTS here, big question. Maybe those are connected. So there are things that we can understand more about the nuclear strong force, and that helps us understand nuclear processes. And then finally, you might say, well, let's go bigger. Well, can we connect gravity? It's not clear that we can. Maybe nature is such that it is distinct. Maybe this is just warped space-time. Maybe this is related to warped space-time. But this would be the toe. So we got the guts, but now we got the toe. I don't know why toes, which is the theory of everything, fundamentally. So it's kind of cool. It's neat. Still, if you're doing engineering, you don't get lost in this kind of stuff because you're not going to get anywhere. You got to talk about contact forces, strings, springs, normal force, and friction. So that's neat. Let's go over here, and I want to straighten out some language. Please, straighten people out. I don't know. I guess it's fine. But people talk about G forces. We'll get into that with circular motion. And it's not really what they mean. People talk about 0G and weightlessness. So we often talk about orbiting. If you're orbiting in the International Space Station or something, or you're falling, people talk about the state of 0G. People in 0G. If you watch the movie Apollo 13 with Tom Hanks, done by Ron Howard, you'll see people floating. You'll see people floating. Oh, it's 0G. Well, what does that really mean? I mean, what does that G mean? Is that acceleration or force? So people really confuse this. Is this zero force of gravity? Well, if you can experience this just by falling. So if you have this attached here and you drop, we have proved that they will fall together. And if they fall together, then the scale doesn't have to hold it up. And the scale will read 0. Whether it's this kind of scale or this kind of scale, as they fall, it'll read 0. And so when people say 0G, they actually mean usually that you're falling, or you've got an acceleration of free fall. So what they mean is that the scale force is 0 and it feels as though you're floating. Maybe deep in space you're floating, but that's not that common, right? And certainly not in orbit. So usually that's what that means, that there's no support, but it does hurt when you hit. So if the cable of your elevator breaks, or you go to an amusement park and you got one of those drop zone type things, it's great, but at some point they got to slow you down, hopefully gently. And so you could say, I'm experiencing 0G. Really? Because G whiz, it'll hurt. You're accelerating. There is a force of gravity because you're near the surface of Earth. So what exactly does that mean? Well, they film that by taking an airplane and then they cut the engine so they float up and float down. So within the airplane, things float. But you haven't turned off the force of gravity from Earth, clearly. So we'll talk about that in a second a little more. This also can be called weightlessness, a term I'm not very fond of either. Again, we talked about weight, meaning two different things used two different ways. So either if you're weightless, there's no force of gravity, which may be somewhere deep in space, but if you're in orbit, are you accelerating? You're turning. So what's exerting a force? You feel like you're falling, everything's falling together. And so the answer here is absolutely not true in orbit, that there's no force of gravity. In fact, the force of gravity for a close orbit is pretty close to the force of gravity here. You can have more distant orbits, and you will get a weaker force of gravity. So you're not weightless in orbit. People call it that. What that means is that the scale force is 0, and everything in orbit is, again, falling together. So let's talk about that in a moment, or right now. So we go over here and take a look at our cases, which we studied in kinematics. You can drop an object, and you can shoot an object horizontally. On a flat surface, on a horizontal surface, what you'll find is that they land together. And so if you shoot it with a low velocity, it'll kind of go like this. Right? Why? Well, first, we're going to think independently about vertical and horizontal motion. That's the beauty of it. We divide and conquer our vectors. So the vertical fall is here for the one dropped, and the vertical fall for the one shot is still here. They both start with a vertical velocity of 0. And so they will both take the same amount of time. In that time, the shot object will travel horizontally. If you shoot it faster, of course, in that same amount of time, if you're going faster this way, you're going to land farther away. And obviously, if you shoot it faster, you will land farther away, but all in the same amount of time. Because we can do the vertical, and the vertical is identical. The only thing different here is you've got a horizontal constant velocity motion. So now on Earth, what about orbits? In orbit, which we're going to get to very shortly, next up, circular motion. When you shoot something from a mountaintop, you can imagine this case like a ridiculously tall mountain, because keep in mind Earth's atmosphere is thinner than that line. You go up 7 miles, you're past most of the clouds, right? You go up 200 miles, you're past everything-ish. And then so you got an orbit of 250, 300 miles. You got no air drag or anything, and you're up there. So let's just shoot this guy in this imaginary way. And what happens is, of course, if you drop it, on the one hand, it'll just fall to the ground. And very near to the surface, it seems like it's flat. So we shoot it now slow, and what happens is the object falls, but our ground curves away, and so it falls and doesn't hit until there. Now I shoot it faster, and it's going to go farther, just like up there, but the ground is curving away. Then if I shoot it really fast, I might get to some speed where the ground curves away and you're just chasing the ground and you never hit. But you are constantly falling in orbit, because there is, the free body diagram would be a force of gravity. So if you want to call that weightless, what you're saying is the scale force is zero, not the force of gravity is zero. If the force of gravity, all of a sudden, if Earth said, I'm tired of this, I'm going to stop pulling on you, you just do what you want, then you're going to go straight with Newton's first law of equilibrium, not the law of inertia. Any object, your cup of coffee, your dog that you brought up in orbit with you, and your iPod Touch. So everything will go straight if you turn off gravity. So you see something accelerate, there's got to be a force of gravity. That's not force of gravity-less, it's scale forceless. And so in orbit, you'll float around and you'll step on the scale and say, wow, I've lost weight. In fact, I have none. That's really weird. I must be light. I am a beam of light, or maybe not. So, okay, cool. That's just a little fun facts. I think I want to mention one more little fun fact and get you thinking, and that is about a contact force. Again, contact forces ultimately are electrical in a deep sense, but no need to say that. So with friction, there's kind of a neat thing about friction. And let's do this as a drawing, but I can imagine this surface, it's got different material here, and then a different material here. So you can do these experiments and you can see what force is required to accelerate it, how much, measure distance, measure time, calculate acceleration. So you can imagine this case where you've got, remember, the strength of the force of friction could be zero. It could be force static with no equation. It could be force static where you're about to slide relative to the surface, mu s n, or it could be sliding relative to the surface, mu k n. And the interesting thing is, and you can get this intuitively, if an object is sitting here, while there is roughness, the friction is zero. As you push a bit, the friction grows, which means that the grooves on one surface go into the grooves in the other, and they push structurally. And then when they're about to slide, by pushing harder on it, and you've got then a friction going opposite, the friction grows, still in balance, but right about to slide, Fs max equals mu s n, where n is, of course, the normal force. But this tells you how much they're squeezed together more, you get more friction. Finally, you get it to go, and you have this experience. It's pretty easy. Once you get it going, it slides more easily. And so that tells you something, that you can actually reduce that force and keep it sliding. And so in that case, and if you keep it sliding, say with acceleration equals zero, but v not equal to zero, then these two forces are balanced, yet you don't have to push as hard once you got it going. And that means that Fk equals mu Kn is less than this, which means that mu K, roughness factor, no units, is less than the static coefficient of friction and kinetic coefficient of friction. And you can see that. So that's one interesting thing. And how do you do it? Well, people usually just make tables. They do the experiment to find this out. They don't imagine exactly how the roughness is. So that's one thing. The other thing that's interesting and maybe not obvious is that the result is independent of two things. So the friction kinetic is independent of your velocity. Unless you get too fast, you can heat up the surface and things like that. But generally for lab type, in most cases, that is, it doesn't matter how fast you're going, that's always a constant. So that's a really important thing to just know, that it doesn't matter how fast you're going, that's a constant. The other thing that's interesting is that it is independent of the surface area in contact. So that's maybe a little bit surprising, that if I have this much contact surface, I get the same friction if I have more contact surface. So there's one to really think about physically. Why is that true, that I get the same friction here as I do with more surface? Now, the real world, surfaces may not be evenly rough. So you might hit a slick patch over here or a rougher patch over here. So here you might get less variation, but that could be good or bad. You might hit slick or you might hit really rough. But with the same surface, you get the same friction independent of the contact area. Think about it in terms of the normal force per area, how much you're supporting there. And I'm going to leave it there as a discussion. Okay, cool.